there are a couple of really important properties with matrix transformations. Okay, so let's let T from Rn to Rm be the matrix transformation T of x equals A times x. Okay? Then I want you to observe a couple things. Let's take any two input vectors from our domain. So let's let vector u and vector v be in Rn, and choose some value k that's a scalar. Then, if we take T of k times u, we get, by definition, that's A, matrix A, times ku. And by associativity of scalar matrix multiplication, I can pull the k out to the front. All right? Which means that if I scalar multiply a vector, I just scalar multiply the result of that vector also after I apply the transformation, right? In other words, it doesn't matter if I scalar multiply the vector before I apply the transformation, before I multiply by matrix A, or after I apply the transformation, after I multiply the matrix A. And so matrix A times u, that's just T of u. Okay? And then one more observation here. So if I have T of u plus v, then that'd be A times the sum u plus v. And by distributivity, if I distribute matrix A in, I get AU plus AV, which is just T of U plus T of V. Now I want to be very clear that this property doesn't generally hold for any kind of function or even any kind of transformation, but for matrix transformations, these properties hold. Okay, so in this latter case, it doesn't matter if we sum up the vectors before we apply the transformation, or if we transform the vectors first and then sum them up. Now, these are very important properties because of what it means for linear combinations of vectors. Okay? Now let vector w be equal to A times u plus B times v. So that is, vector w is a linear combination of vectors u and v. Okay? Then if I want to find the transformation of vector w, well, look what happens. If I use the linear combination of w, tau plus tbv, I know that if I have a sum of vectors, I could take the transformation of the two vectors individually and add them together after. So this is equal to t times au plus t times bv. Okay? And then I have a scalar times a vector here. I have a scalar times a vector here inside the transformation. And I know if I have a transformation of a scalar times a vector, I could take the transformation first and then multiply by the scalar afterwards. So I'm going to just pull out that scalar from the transformation. Okay? So notice what just happened. If W is a linear combination of vectors u and v, then the transformation of W is a linear combination of the transformation of u and the transformation of v. And the coefficients for the transformation are the same. Our observation is if T is a matrix transformation, then T preserves linear combinations. Okay, that is, we use this word preserves when it's true before and it's true after. Okay, so if we have a linear combination and we apply T, then after we apply T, we still have a linear combination. Okay, we call a transformation that does this. We call a transformation that does this a linear transformation. So a matrix transformation is a linear transformation.